Welcome to the Logical Foundations of Cyberphysical Systems course and its accompanying textbook. In this lecture, we are not expected to already know what a cyberphysical system is. Rather, I will give you an overview of what we are going to study in this course, and most importantly, in how many ways that is important to you and to society by and large. In this video sequence, I will talk about many of the important aspects that are discussed in the textbook as well, but of course the textbook goes into a lot more detail on many of the topics, especially in its appendices. First of all, what is a cyberphysical system? By way of an example in the air. Suppose that you are the pilot of this aircraft and you got into a difficult situation with other aircraft being rather nearby to you. Or suppose you're designing the computer for this aircraft where the pilot did not pay attention because he was stressed out and got very close to other aircraft. At this situation, it would be very useful if you could quickly predict that flying straight on, flying a slight left turn, flying a slight right turn will all be too dangerously close to the paths of every aircraft, but rather that flying a strict right turn is the best possible way out. But of course, at the moment when you're here, you don't have enough time to sit down and carefully plan out all the trajectories that the aircraft could be taken, but you have to reach the right decision very quickly in a split second. Computers are very good at reaching those decisions in a very quick way. But they also have to be right about it, because otherwise the advice that the computer systems give to the pilot in the air is not actually going to be helpful. And of course, if the pilot got into such a tight situation here, chances are that when he gets out of there, he could still get into other conflicts with other aircraft, and of course whatever advice the computer system gave back here needs to be compatible to make sure that future paths are still possible that avoid other potential conflicts with other aircraft, and everything works out fine at the end. This, by way of example in the air, is the Cyberphysical Systems Challenge, where cyberphysical systems, or CPSs, combine cyber capabilities such as communication, computation, and control with physical capabilities such as the very motion of this aircraft through the air to solve problems that neither part could solve alone. Because of course, without the computer, it's very difficult to control modern aircraft, and it's particularly helpful to use computers in situations to avoid such potential collisions in the air. But without the physics, flying an aircraft also wouldn't be a whole lot of fun either. This is just one example of many cyberphysical systems applications, because once you realize what a CPS is, you will find them everywhere, with prospects of improved safety and efficiency in many ways. For example, in driver assistance technology, as well as fully autonomous self-driving cars, pilot decision support systems, autopilots, unmanned aerial vehicles that are supposed to fly on their own for extended periods of time, or for the periods of time where the remote pilot cannot directly supervise them, train protection systems, or whatever happens when you're using robots near humans as opposed to locked away in a separate facility of an industrial setting where no humans were ever allowed to go. In all of those settings, cyberphysical systems, and in particular their computer parts, are used in order to improve on a situation. For example, in the car situations, computers are trying to help drivers be better drivers and avoid potential safety hazards or collisions on the roads. But it's very important that they're right about it. In certainly self-driving cars, where we fully yield control to the computer, it is very helpful to have such technology, but it's, again, very important for for the self-driving cars to actually be very reliable. Otherwise, driving on our own would be significantly more helpful for us. Pilot decision support systems, they better be right. Autonomous technology for controlling UAVs or drones had better be right. Train protection systems are really useful in order to save lives, but they also have to be right about their decisions. And when we let robots act and maneuver near people, it is very important as well to make sure that their interactions with people meet safety requirements. In other words, while CPSs promise a very transformative impact, it's also super important to make sure that this transformative impact is beneficial and not the literally transformative impact of a kinetic collision of one car and another one. So we need to make sure that CPSs actually make the world a better place by convincing ourselves that their designs are really safe. What that means for us is that we need an answer to the question how you can trust a computer to control physics. And I do not mean that in the sense of the computer controlling the laws of physics, because these are really quite non-negotiable. I just mean that in the sense of the computer providing appropriate inputs into physics to get physics to do what the computer wants via actuators, changing the torque and rotation of the motor, or think of the rudder and aileron of an aircraft. Whether you can trust a computer to control physics depends, and it depends on how it has been programmed, but also on what will happen if it malfunctions. For example, if you have a GPS-guided, Bluetooth-controlled electric toothbrush, there's really very little damage that it can do to you. But the same is not true on a car or an aircraft that you are flying in or driving in. So the rationale behind the course that we're taking here is that computers would certainly earn our trust that they can control physics if only they came with guarantees. And such safety guarantees do require solid analytic foundations. Also, we would like those foundations to be useful for all of the application domains, to be a common foundation. We don't want a special mathematics that only works for trains, but doesn't tell us how to correctly drive a car or fly an aircraft. Granted, the concrete answers will be very different. Just because you know how to ride a bike doesn't mean you would be able to fly an aircraft. But, of course, we should be using the same kinds of mathematics to come up with the answer for these systems. Now, the foundations have absolutely revolutionized the digital part of computer science and indirectly our whole society. But we do need much stronger foundations as soon as that software reaches out into our physical world, because our very lives are at stake. Or as Jeanette Wing phrased it, how can we provide people with cyberphysical systems that they can bet their lives on? That's the real question. In other words, for us, the conclusion is that cyberphysical systems are so important that they deserve nothing less than a proof as safety evidence. And I hope that that is a welcome conclusion for you. How we make such proofs happen for cyberphysical systems is precisely what this course and textbook is about. The key secret insight in order to make cyberphysical systems analysis happen is that they actually are what I call multidynamical systems. By that I mean CPSs are characterized by multiple facets of dynamical systems. Not just one, but many of them. For example, they will have aspects that come from discrete dynamical systems, systems that take one step at a time, just as what computers are very good at. But they also do have aspects that are continuous dynamical systems in nature. Things that change continuously over time, such as the very motion of the aircraft through the air or the way how a car drives down the road. CPSs, however, may also be subject to other dynamical systems aspects. For example, of adversarial dynamic, whenever multiple systems meet and can't necessarily rely on what exactly they will be doing to one another. Think of it this way. If you're controlling one robot and I'm controlling another robot, then you may not know exactly what my robot is trying to achieve, and I certainly won't exactly know what your robot is trying to do. Under those circumstances, your robot will still be safe if you find a way of controlling it such that it will achieve its mission safely, no matter what my robot is trying to do and no matter how my robot is being controlled. And that is one example where an adversarial aspect enters the game. In this particular case, not because my robot is trying to actively hurt yours, but just out of ignorance. You don't know exactly what my robot is doing, and I have no knowledge of what your robot is being programmed like. But adversarial dynamics is just one way of resolving certain uncertainties that exist in the system. Other dynamical systems features come from non-deterministic dynamics, whenever you simply don't quite know, but you can also have stochastic dynamical systems aspects in it. Now, the point being that CPSs are really multi-dynamical systems. And by the minute you realize that the best description is exactly like so, as a function that combines many of these dynamical systems aspects with one another, then not only have you simplified the description as a composition of individual dynamical systems aspects, which by definition are individually easier, but you've also almost solved the analysis question if you simply continue to exploit this compositionality in the description also for the analysis purposes, and that way tame the otherwise overwhelming complexity of cyberphysical systems by analyzing the whole system as a function of the analysis aspects of each of the parts. And that way you carry over the descriptive simplification of cyberphysical systems out of a composition of individual aspects into an analytic simplification as an analysis of the individual parts. And that is precisely what logic is extremely good at. Why? Well, because in logic, the very meaning of logical operators are by design compositional. For example, the formula A and B is true exactly when A is true and when B is true. Moreover, a proof of a formula A and B consists of a proof of the formula A together with the proof of the formula B. What we now have to do is make the exact same compositionality both in the meaning as well as in our proof and reasoning principles work out, just not for the AND operator, but for all the operators that are important in cyberphysical systems. Indeed, if we look at the multidynamical systems, we already find many important subclasses of multidynamical systems. One very prominent one is that of hybrid systems that are living in the intersection of discrete dynamical systems and of continuous dynamical systems right here. And in fact, the first part of this course will be covering only the hybrid systems aspects of it because they're a very fundamental basis. But later on in the course, we will go back to this multidynamical systems idea and realize that adversarial dynamical systems aspects are also of interest, in which case we will find the hybrid games subclass. Just letting you know that what I'm presenting here also extends beautifully to stochastic dynamical systems aspects in stochastic hybrid system settings when you have a bit of a more crazy randomized dynamics in the system. But the multidynamical systems idea is really more general. It's the fact that you can have additional dynamical systems aspects, such as, for example, in distributed hybrid systems, where you understand that in order to describe a whole fleet of cars on a road, you best not just look at it flatly as a hybrid system, but you also understand its distributed systems aspects, because, of course, If this is one car that you may describe as a hybrid system, here's another one, and here's another one. And it is important to realize that each and every one of them is an individual hybrid system, but the collection of all of them together also satisfy important distributed systems phenomena. Because, for example, even if the structure of all of the cars are alike, their concrete design, their concrete position, their concrete velocities, their concrete acceleration choices may all be a bit different. Now, in order to give you a better sense of how the most important hybrid systems angle of it works, let me zoom in to the idea behind the hybrid systems models, which of course we will see in a lot more detail developed in the next aspects and chapters of this course. If you take my favorite hybrid system, which is the Wally robot, then the Wally robot may want to move in a corridor environment such as our building here in the Gates-Hillman Center, where people have strategically placed concrete pillars in the building to make sure that people bump into them, and since robots see people do this, they want to try it out as well, but it turns out that the Wally sensors get damaged rather badly if it would be running into this concrete pillar, or into the walls for that matter. And so if we're trying to understand the behavior of Wally, we quickly identify that Wally has two characteristically different types of dynamics. The one is the discrete dynamics, coming from decisions, such as, for example, when Wally is moving along here, at some point he might notice, oops, I'm going too fast because there's an obstacle right in front of me. Maybe I should decide to slow down. As you see over here, that his acceleration is 0 for quite some time, but then he decides that he needs to brake. After a little while, he decides that braking wasn't hard enough, he needs to brake harder. And after that time is over, he decides that the situation has resolved and he can accelerate again, such that after a little while he decides that keeping his velocity constant is an acceptable choice again. But that was a discrete dynamical systems aspect. It was a decision that Wally took. Other aspects of it are where the velocity of the robot and the x and y coordinates of the robot are changing as continuous functions over time. These are continuous dynamical systems, and of course a discrete model of Wally hopping around in discrete space would be a very poor rendering of what is really going on. Likewise, for example, the angular velocity, corresponding to the left and right curving of the robot, is also a matter of decision. Wally at some point decides that he wants to turn right or turn left, whereas the concrete direction that the Wally is moving into is a continuous function over time. And it's not so important what exactly are the discrete dynamical systems and the continuous dynamical systems aspect in this system. What's more important that here we look at an entire framework of hybrid systems that mix and match discrete dynamics and continuous dynamics, such that during our process of modeling, analyzing, and designing our systems, we can freely choose and move from one understanding to another as we see these become better fits for what we're trying to do. Now, let me also quickly distinguish and then identify two related but different notions. The one is that of the hybrid system, and the other is that of the cyberphysical system. So both are very related but also different. A hybrid system is a mathematical model for a complex physical system that comes with ways of interacting discrete dynamics and continuous dynamics. But the source is a mathematical model, whereas a cyberphysical system comes from a technical characteristic. A canonical cyberphysical system is implemented as, for example, a distributed network of computerized control systems that are controlling a physical system with communication, computation, and control aspects of physics. Of course, the mathematical model of a hybrid system fits very well with many important aspects of CPSs, which is also precisely what we will be studying first in this course. But the mathematical model of a hybrid system actually can be used in other circumstances as well. For example, in biological applications, where you have discrete activation of genes, but continuous dynamical systems aspects of gene expression, for example. But the cyberphysical systems aspect also could involve a little more than the hybrid systems aspects, for example, the hybrid games or the distributed hybrid systems aspects. Having said that, because the hybrid systems mathematical model and the cyberphysical systems technical model fits so well to one another, I will simply, for the first two parts of this course, identify the two notions. Whenever I say CPS, you can, until then, hear hybrid system, and whenever I say hybrid system, you can, until then, hear cyberphysical system. Only in the third part of this course will we begin to tear the two notions apart again. Now, at this point of a lecture, you may want to ask yourself more questions. So what are other cyberphysical systems that are around us, and in what way are they important to us? And you can look at this more broadly and ask yourself what cyberphysical systems aren't around us yet, but will very well be in the future, or which ones would you like to design? And then you can also ask yourself the question, which of those cyberphysical systems will we want to trust with our lives? In this course, you will be given the opportunity of answering some of the typical CPS design and analysis questions by way of a robot example that we will be increasing throughout the semester. The first challenge in Lab 1 will be to design a robot that safely will make it to a charging station simply by moving on a straight line in order to make the motion easier for the system. And its goal is to get to the charging station without falling short. Maybe stopping here would be a bad thing to do, but it's even more important for safety reasons that the robot stops at the charging station and doesn't continue to move on, which, for example, would be a very bad idea if there would be an obstacle right after. In this lab, you will first design a controller, design a model of the physics, and then verify that your controller is indeed working safely and correctly for the purposes of this model. In the second lab, you will implement a follow-a-leader protocol for robots where, for example, if you're controlling this robot and we're controlling that robot, and both of them are moving down, then you, of course, don't know exactly what the robot in front of you will do, but your job is to follow this robot at a safe distance. Don't fall behind too much, but also don't collide with the other robot. So, for example, if this robot and other obstacles are happening, then your job will be to make sure that you follow without ever possibly colliding. Again, you will first design a model of the physics in the controller and then convince yourselves by verification that your design is really a safe one. In the fourth lab, we will be looking at motion that is no longer restricted to just moving on a straight line, but with much more free motion of a robot through the planar world, where other obstacle robots could be moving, and you need to make sure you stay clear of them no matter where they are in order to make sure that, for example, they move freely, as opposed to in this scenario where both of them collide. Again, you will be designing and modeling and then verifying the system in order to make it easier for you to transition from the motion on a straight line, which is basically a robot on rails, to the free motion in the plane. We will, in the middle, ask you in the third lab to design a robot that can safely follow a circular track, which you can understand as a part of what the robot might be doing back there as well. But your job is to make sure that it doesn't leave the circle and it doesn't collide with obstacles that it might be finding on the circle. Again, you will be designing, modeling, and then verifying the systems. in order to give you more appreciation of that, you will be designing and verifying controllers for robot obstacle avoidance, where your decisions of the robot will be to accelerate or brake, which is the discrete dynamical systems aspect, and the continuous dynamical systems aspect will be the motion in one dimension on a straight line with velocity and position changing. For example, here's a scenario where you will have a charging station right at the wall, and of course you need to get there without falling short. For the fourth robot lab, for example, you will not only have to worry about position and velocity, but you will also have to worry about the direction that your robot is currently moving into and the angle of velocity with which it is moving, which corresponds to how strongly it is turning presently. So in addition to acceleration braking being a decision of the robot will also want to steer by discrete decisions. And your dynamics will no longer be essentially a one-dimensional state space or one-dimensional motion space, but a two-dimensional motion space, of course with corresponding velocities in those directions as well. And the challenge gets bigger whenever other robots move in the neighborhood as well, because when the Wally robot is moving on a foreign planet, then whenever he meets another Eve robot, he doesn't exactly know what Eve will be doing. So things get more interesting, which you will have an opportunity to explore in the fourth lab as well. Other aspects you will be exploring in the labs are how your robot is being controlled, how it respects reaction delays, how it interacts correctly with an environment, with obstacles, other agents, and how it deals with uncertainty about what the other agents could be doing in its environment. After this overview of cyberphysical systems, let me zoom in to the course design for the Logical Foundations of Cyberphysical Systems course. First of all, you will notice that cyberphysical systems bring together many exciting but also non-trivial areas of science. For example, there's many aspects of algebra that are helpful, there's many aspects of analysis that are helpful. If you're dealing with stochastic hybrid systems, there's stochastical systems aspects. Numerical aspects can sometimes be of relevance as well. There's many algorithmic parts, and we will see numerous areas of logic that are influencing the logical foundations of physical systems. Don't panic with all this background. There's two ways of taking you through this. The one is the onion model, where we start on the outside layer of this dependency. We unpeel one layer at a time, and we basically progress to more inward circles whenever all the prerequisites have been met. The way how you would do that in a course is you first go off and study all of computer science, then you go off and study many areas of mathematics, then you study all of engineering, and we ultimately talk about CPSs in the big finale. Other approach of teaching cyberphysical systems is the scenic tour model, where we will start right at the heart, cyberphysical systems, and then we will go on scenic expeditions into various directions of the dependencies in order to basically explore the scientific world around us as we find the need to actually do. The advantage of that is that we stay on cyberphysical systems the entire time, and we also leverage cyberphysical systems as the guiding motivation for understanding the various other connected areas of science. Of course, the twist is that this requires a very careful prerequisite management in order to make sure that we pull in the intuition of other areas in the maximally efficient way right when we need it. Because this approach is much more effective, we will be following the scenic tour model in this course design. One aspect that is absolutely fundamental of this course design is basically computational thinking for cyberphysical systems. Computational thinking is what Jeanette Wing called the influence of this type of computer science thinking into many other aspects of the world, which here in cyberphysical systems leads us to conclude that we will worry about logical scrutiny, formalization, and correctness proofs that are absolutely critical for cyberphysical systems right from the get-go, as opposed to as an afterthought, because if we do this too late, our system designs may already have gone wrong and maybe they're hard to fix. The phenomenon is that cyberphysical systems, even though they are so powerful, they're also subtle enough that they're very easy to get wrong. You cannot just take a CPS and retrofit it for safety, just as it's very hard to take a system and retrofit it for security. In other words, the logical aspects of a CPS are an integral part of the CPS design, and they're absolutely critical to your understanding of the intricate complexities of CPSs. The benefit is also that we tame the complexity of CPSs by working with a very simple and logically designed programming language for the core aspects of CPS designs. Other learning goals are that foundations is an all caps word essentially in this course. We will worry a lot about what is the core essence of cyberphysical systems, as opposed to undoubtedly also important technical aspects of how specifically they're being put together. In modeling and control, we will want to understand the core principles behind cyberphysical systems. We will learn to develop models and controls for these and identify the relevant dynamical aspects of a system. For example, are discrete dynamical systems aspects important? Are continuous dynamical systems important? Will adversarial dynamical systems aspects be important, and so on? Because not all of them are equally important in every application. On the computational thinking side, we will learn how to identify safety specifications and critical properties of cyberphysical systems. We understand the very important role of abstraction in system design. We will learn how to express preconditions and postconditions for cyberphysical systems models in order to be able to express, state, and ultimately use when it is safe to turn on a CPS and its various components. We will leverage the design by invariant principle to use logic to design the correct controller from the get-go. We will reason rigorously about CPS models as opposed to just by an intuitive judgment. You will learn how to verify cyberphysical systems models of appropriate scale. In the CPS skills area, we will understand the semantics of a CPS model and develop an intuition for its operational effects, which is very important in order to be able to exactly understand how the various parts of a cyberphysical system fit together and what its possible behavior all could be. We will use logic to identify control constraints for a cyberphysical system, to identify what does it need to do, when does it need to reach which control decision to make sure that the cyberphysical system does what I want it to do safely. We will understand opportunities and challenges in cyberphysical systems and also their verification in order to get an appreciation for what kind of questions can be answered well and what kinds of questions needed slightly different phrasing in order to be manageable. And as almost unintentional byproducts, we will have a well-motivated exposure to numerous other areas of mathematics and science that we will see in action. And throughout the textbook, you will see little expedition boxes that invite you to follow up with links that you may already know from your background or links to other areas of science that you may have become excited to study further because you just learned about their use in cyberphysical systems. Here's a pictorial representation that we will be using throughout the course of the computational thinking aspects that we would like to learn about, the modeling and control aspects we would like to learn about, and the cyberphysical system skills aspects that we would like to learn about. The course outline follows the outline of the textbook, where in the first part we will look at the elementary cyberphysical systems models. We will dive into what we need to learn about differential equations and their domains, how control aspects and different choices are expressed in hybrid systems, what important safety considerations are and how we state and express contracts, correctness conditions for cyberphysical systems. Then we will switch gears and take logic serious and use it for rigorous reasoning principles about cyberphysical systems. Take a look at truth and proof principles for CPSs. And then, after having fully understood many of the simpler operators of hybrid systems, we will take a look at feedback control loops in cyberphysical systems, which are, of course, absolutely important in their design, but it simplifies our understanding of it if we postpone the handling of those questions for a little while. Having done so, we come back into events and responses for event-triggered control, and we will understand time-triggered control and reactions, and the important phenomenon of delaying systems. Walking away with an appreciation for elementary cyberphysical systems, that was the easier part, where we assumed that the continuous dynamical systems aspects of the CPS are not quite so bad yet, but still solvable, which limits our scope in terms of what systems we are able to analyze. So in the second part, we will take a deep dive in differential equations analysis techniques in order to enable our CPS models to rigorously design behaviors for more sophisticated motion dynamics or other physical dynamics or chemical dynamics as well. By looking to differential equations and their invariant principles, differential equations and proofs. Also a very spooky technique called differential ghosts, which however is extremely powerful, and some exciting aspects of proof theory. Walking away with an understanding overall of advanced cyberphysical systems, we will then become more playful in the third part of the course by looking at adversarial dynamical systems aspects in cyberphysical systems by way of studying hybrid games, and ultimately finish up in the fourth part of this course with comprehensive CPS correctness arguments. So what is it that we need to do in order to implement them correctly? What is it that we need to do in order to correctly relate the model of a cyberphysical system to an implementation of a cyberphysical system? And what is it that the reasoning ultimately depends on? You will find that the materials of this course provide many different entry points and different orders of reading it. Of course, the beginning is quite fundamental, but then we essentially branch out into an understanding of the elementary cyberphysical systems aspects, understandings of advanced cyberphysical systems aspects with a deeper understanding of differential equations reasoning, and adversarial cyberphysical systems aspects, each of which are independent for exploration, as well as comprehensive cyberphysical systems questions. Let me briefly review the labs you will be doing. First, you will worry about basically robots and rails by first getting robots to just move on a straight line and then get to the charging station. In the second lab, you will consider robots moving on highways by following the leader with both event-triggered control and with time-triggered control, both of which are very important paradigms in control. Then you will look at robots on racetracks, staying on the circular racetrack and slowing down in order to avoid obstacles. Then you will look at the motion of robots in a plane with both obstacle avoidance and ultimately also what happens if your robot is meeting a rogue bot, another robot that isn't moving in the way you would like it to, and your job will be to make sure that there are no collisions with moving obstacles. The most important and exciting fifth part of the labs is where you will have an opportunity to do a self-defined final project or a star lab that only has two rules. It's got to be related to the topics of this course, and it has to be fun. You have to really want to achieve this. One of the most exciting aspects of it is that you will have an opportunity to present your final course project to a panel of CPS verification validation experts at the CPS V&V Grand Prix at the end of the semester, and you will be competing for prizes that are donated by judges. For example, here in 2016, by a number of industrial companies, or for example NASA as well. So wrapping up, what we would cover in this course is the logical foundations of cyberphysical systems, because they make such a big difference for CPSs, but also vice versa. There's many exciting aspects of logic that you only ask because you're studying CPSs. So this course is both exciting to you if you're interested in CPSs, but also exciting to you if you're interested in logic. The course provides strong analytic foundations, practical reasoning advances in terms of Roll-Upper-Sleeves theory improving, very significant applications as well, and is an opportunity to catalyze many exciting areas of science and bring them together in ways that otherwise wouldn't happen. The key secret design principles behind the course are, on the one hand, the multi-dynamical systems principle, that systems are described as a combination of simpler dynamical systems aspects, which, because they're individually simpler, tames the otherwise overwhelming complexity of the system. And the course also provides many exciting verification and validation challenges where numerous wonders still remain to be discovered.